This video is the third installment in a series showing how to approach calculating the pH at various points in a weak acid strong base titration. We previously calculated the pH of the given acetic acid solution prior to addition of any base and after 10 milliliters of the sodium hydroxide solution was added. In this video, we will calculate the pH of the solution after 25 milliliters of the sodium hydroxide solution has been added. Calculating the pH of any titration requires you to initially treat the situation as a stoichiometry problem, which means that we first need to determine how many moles of hydroxide ion was added to the solution. To do this, we will multiply the concentration of sodium hydroxide by the volume of sodium hydroxide added. For 25 milliliters of a 0.10 molar solution, that comes out to being 0.0025 moles of hydroxide ion. Since we can assume all reactions involving strong bases go to completion, we can determine that after the reaction is complete, the solution will contain 0.0025 moles of acetic acid, 0 moles of hydroxide ion, and 0.0025 moles of acetate ion. Since the volume of the solution and the moles of acetic acid and acetate ion have changed, we will need to calculate the new concentrations for both species. This is accomplished by dividing the number of moles of the species by the new volume. In this case, 0.075 liters. We can now treat the solution as consisting of a 0.0333 molar concentration of both acetic acid and acetate ion. We'll set both of these values aside for now because they will become important for the next step, which will be to calculate the equilibrium concentrations of acetic acid, acetate, and hydronium ions. To perform this step, we will write out the equilibrium reaction for the protonation of water by acetic acid and set up an ice table. But instead of initially only having a non-zero concentration for acetic acid in the table, we now have a non-zero concentration for acetate ion as well. Our ice table should state that we initially have a concentration of 0.0333 molar of acetic acid and an acetate ion concentration of 0.0333 molar as well. Based on the equilibrium equation, for every mole of acetic acid that is consumed, we should produce a mole of acetate ion and a mole of hydronium ion. To signify the stoichiometry in the ice table, we will state that the concentration of acetic acid will decrease by x, and the concentration of both the acetate ion and the hydronium ion will increase by x. Now we can combine the values we have for the initial concentrations and the expected changes to give us equations for our equilibrium and concentration. We can set up our equilibrium expressions where Ka is equal to the concentration of hydronium ion times the concentration of acetate ion over the concentration of acetic acid. Plugging in the equilibrium values from the ice table gives us the mathematical equation 1.8 times 10 to the negative fifth is equal to x times, in parentheses, 0.0333 molar plus x over 0.0333 minus x. We can now solve for x by doing some algebraic manipulations and using the quadratic equation, which will give a value of x equal to 1.8 times 10 to the negative 5 molar, which is then also the concentration of the hydronium ion. We can now solve for the pH by taking the negative log of the hydronium ion concentration, and we'll get a final pH result of 4.74. This is the point of the titration where the pH of the solution is directly equal to the pKa of the weak acid.